Job record analysis. So Raf and I are here today to talk about this. Our supervisors were Kiowa, Damien, and Kerry, and they were excellent resources for us throughout this project. It's been quite insightful and interesting. As boring and weird that the words job record analysis sound, they're not the most riveting words in the English language, but without much context, it doesn't really sound that cool. But I think you might change your mind by the end of this. So if we go to the next slide, we should see is so a bit of a background on the project. So the Slurm database is basically how the scheduler scores all the jobs on that are submitted on Massive, and it currently contains about 20 million plus records. This is quite a lot. And if you think about all the different jobs that get submitted every day, it's handling a lot of insert operations, and it gets quite hard to get any data out of it to look at without overstraining the database or causing any adverse effects on people's jobs and things. So we really want to analyze these job submissions to try and get data, get some plots for people, and see if we can find any trends or parameters for jobs. We could guide new Slurm users, new Massive users to better write their batch scripts so that they get their jobs through a bit more easily. And also to kind of provide a new way to interact with the cluster that's not all command line and Linux style stuff. So if we move to the next slide, it kind of sounds a little bit abstract, but a graph, these are two graphs you might be able to see that kind of highlight the ideas we had. So the one on top has the red bars and the green bars. And the red bars are basically from the job time it was submitted to the job time that it was completed. And then the green bars are the time the job actually spent in compute. So you can see that for some different choices of CPUs, numbers of CPUs, what you'll see is that the jobs that waited a long time had certain core allocations. And so if you think about how this data could be useful to an end user, it could be useful if you think about the fact that, let's say you had something due and you knew it was going to take about an hour to run on the system with a particular setting, but you knew you might have to wait an hour for the job to be fully submitted, but you could get it done quicker if you asked for less resources but got through the queue a bit faster just because of your lower asking resources. So this kind of tool could be really helpful to any people that are in a time poor situation or trying to work towards a deadline to get some outputs that they need. So this could be a tool used to game the system, game the scheduler, so that you get your data back as quick as possible. Now this is quite a small sample size, so can't really draw anything from it, but with access to all 20 million records, we would hope that you'd be able to achieve something a bit more useful. And then the second plot at the bottom of this, you should see there's these blue bars, and what they have are the number of jobs that each individual user had submitted over the time period that we gathered this sample data. And what these are kind of useful for is if you think about like a management situation where you're running a team, something that's quite cool about it is you can see who's contributing the most jobs to a particular outcome in a project. Or you might want to touch base with someone that might have been a bit less active over the last week or so. And this could just be used in plenty of team situations to just check progress and contribution. And there's plenty more different ideas we had, like looking at the breakdown of certain people's allocated CPU choices or their resource, or even wall times. And these are just two small graphs, and it's kind of tip of the iceberg when it comes to data analysis you can perform with the detail that these job records go to. So we can move to the next slide, and I want to talk a bit about this process called extract, transform, load, and then the two tacked on the end are analyze and display. So the analyze and display are pretty self-explanatory. It's where we have the data out of the database and we are going to display it to the end users. But the extract, transform, load process is quite interesting because at first glance, and especially to Raf and I, it kind of felt a little bit redundant because essentially what you're doing is creating a copy of the data somewhere else that's accessible. And it feels like a bit of a waste of storage space, but it's not really, if you think about it, once we kind of explain it a bit more. So what we want to see here is the extract, transform, load is like a data engineering term. And pretty much what we want to do is take all the data that we can from the database that exists currently, the SLEM database, and put it in a different database. And now this new database is not handling all these job submissions every second of every day, but it's updated at regular intervals so that it's got more resources to allocate for getting queries, and it doesn't slow a whole system down when you're trying to ask for data from it. And so the extract process is basically where we write some scripts to get the data off the main database at regular intervals. And the transform process is quite simple. It is where we pass the data through some kind of scripts that look at it and check that it's all in the right format for the way we want to store it. And it could potentially perform some small operations on it. It could do some averages or some aggregates. And that could definitely affect the way that the data is interpreted or easily accessed. So instead of having to ask the database for all the data to do the average itself, you might be able to access the average instantly. And that could really streamline some of the analysis processes. And then the load is obviously the final part of this process, which is where you put the transformed data on this new database. And the end goal is to have an offloaded data warehouse. So the data warehouse is similar to a database in almost every way, except it's designed in a way to streamline queries. So it's like, think about like milk on a shelf at a supermarket where you grab the one that's going to expire soonest first because of the way they stack the shelves. So the data warehouse is designed so that complex queries come back quicker. And so from this, the next slide, I'm going to hand over to Raf, who's going to talk a bit more about database schema, which is where data warehousing comes into its own.
Beautiful, thanks, Mitch. So, like Mitch was saying, with loading all of that transformed data onto a data warehouse, we had to come up with some sort of schema into how all the data would be, I guess, related or the format it's stored in. Now, there were multiple options for this to be conducted. So like the original format is just like a flat table, non-relational style where each of the records are individually entered into the warehouse. And now this isn't probably not useful for us at all, given that we wanted to find some relationships between the multiple parameters and that sort of logical grouping that we can do to do some analysis on later. So that's why we decided to come up with logical groupings of all the parameters that existed to us with different branches that connect to each other with different primary keys and surrogate keys and the like, where it's sort of in nodes and you can link to each other based on the sort of group that you wanted to refer to. And coming up with this led with some tougher decisions, or I guess, sorry, let's just go back to the, so this is essentially, this is the, that was the database we came up with, but the questions we had to ask ourselves were, I guess, what's the most efficient sort of format or linkages we can do to be for querying? If we're going to be running this with a lot of records, it might slow down the process and that sort of thing. And there are enough fields that we're given in the data that can be distributed into different nodes. So yeah, if you just go to the next one real quick, Midge. Now this is the format that it came in. So Mitch only drew up, I guess, four parameters, but job ID, user, there was also the job name, which inside the job name, you could see the project it was related to, and then all the time related parameters, so start, submit, end time, wait time, as well as all the computational data information like the CPU usage, whether or not they use the GPU and how much RAM they use. So if you go to the next one, what we came up with is this table here. So going from left to right, it's sort of, we've tried to split them as logically into how each of the parameters are grouped. So starting with the core is the job ID, and that's going to be the secret source to everything. I guess that's where you what you query to find each individual record, and from there it can link to, or each job obviously has its own times that it conducts, and is related to a project, which is the project info table, as well as the user who submitted it, what projects they have running, what jobs they've done, how often they've used it, which are the nodes they use most frequently, that sort of thing, as well as the individual job information. So like I was mentioning before, the computational data that's necessary, I guess that's related to the project as well. We found that each of the projects had the same amount of resources allocated to it, even though they're all different jobs. So that could be linked underneath the project info. And I guess you could go back and forth and figure out all the resources used. But that's the schema we came up with, and I think it represents well what you can do, especially like we were mentioning before with some of the metrics like wait time versus, or like the total time it took to conduct a job versus the resources you allocated to it. Cool. Thanks, Mitch. Go to the next one. I think I'll hand back to you to discuss the Nectar Cloud instance.
Yeah, sure. So we set up a prototype database on a Nectar Cloud instance with a fair few resources. I think it's got like 4 gigs of RAM and 30 gigs of storage, which we deemed more than adequate to handle like our prototyping process. And pretty much it's got 700,000 records on it currently, which we were luckily granted by Damien. He got them off the SLAM database, and which is less than 5% of what it's finally going to have. And the current schema that's working under, the current table structure, is flat. So 2 slides ago, I'll show you it again with just no relational aspects, just flat database. Everything's in one row, and you just query each field individually. So low efficiency in terms of relational database style of things, but very simple to code up and get working quickly so that we could trial some things and see how it worked. And we had actually really great performance with it, with this flat table. So we currently, I guess the next quest is to get access to more data and see how far it goes with this less efficient approach, and whether or not it warrants the complex schema, or that we can get by without it. So there's a few tough decisions to make down the track. But the ultimate thing is that we've got this prototype working, which is quite nice. It reads in the data really well, doesn't really have many issues. And we just want to get more data on it so we can see how it performs with maybe 1 million records or 2 million, or until we kind of get some performance drop of data, and then we can decide whether waiting for maybe 10 seconds to get a complex query back is okay, or if not, then what can we do to change that? And so that's kind of where we're going to head off with the project. And I think I'm going to pass back to Raf to talk a bit more about the future.
Yeah, and just going off that, so like Mitch was mentioning, when it gets too big with the queries, it might take a little bit extra time. I guess the trade-off, or like not the trade-off, but the good thing about the way that this project is styled is that since we're only going to be extracting data, we plan to do it every week with the consolidation at the end of the month to make sure that we haven't missed anything. Now, that means that we don't really need instant, instant queries. I think the way to compare it is with like a couple of weeks ago, monitoring the cluster, they do real-time monitoring and they need the instant responses. But for us, it's not the most vital thing that we get it back instantly. So that's, I guess, a caveat in that we don't, that should be okay down the road. Now, where we see this project going is, we think that there's a lot of potential in this project. We obviously only scratched the surface, and I think that was down to limitations in, I guess, waiting around for things, data, access. So out of people's control. But we hope that down the road that the database can have the relational table that we've created, or something similar to it, so that the data can be put onto it and analyze well. The extractions need to be organized. So like Mitch was mentioning, we've only got 700,000 at the moment, but starting to offload all the historical stuff on the Slurm warehouse, I guess, would be great. Then comes the analysis and display parts. Some of the metrics that we were mentioning before could be done. There's also a lot more that you could do tracking individual user statistics and that sort of thing. So obviously up to where it goes down and who takes over, but that was a few of the ideas we had. And then displaying the insights could be done in a multitude of ways. We were playing around with Bokeh and Matplotlib, and really the world is your oyster with that. And as well as interaction way down the road, if you could figure out some sort of algorithms to best guess your choice of resources based on the times that you're setting, that could work out as well, or the historical relation of how much you requested versus how much wasted time there was and that sort of thing. But that's where we see the project going, and it'd be great to see where it ends up. But thanks for listening. If there's any questions, happy to answer them.
I guess, yeah, if no one else has got a question, with the performance, you sort of said it was decent, but like, do you know how decent exactly?
Not off the top of my head. I don't know like the exact number of how quickly it returned, but for instance, working through Nectar Cloud and basically using a command line to input a query for something that's looking at, I tried to go with what was a more expensive query, so comparing strings.
Yep.
And so we were comparing some strings to get all the data out for them, and I was getting almost instant replies. I mean, that's a very like broad term, but it was good enough that you wouldn't notice if it was like if you'd pressed a command to echo hello world or ask for the query, it came back that fast that it wouldn't matter.
Nice. Yeah. Okay, thanks.